Algebra 2 7.4b, Rationalize denominators with radicals. Now we talked about rationalizing denominators back in Algebra 1 last year. This is going to be with radicals this time. If you've missed the previous videos for Chapter 7, you can click on this video's description to watch those. When we calculate with radical expressions, we usually write our answers without the radicals in the denominator. And this is called rationalizing the denominator. We multiply by a value of 1 to make the denominator a perfect power. So if we've got the square root of the quotient of 1 and 2, square root of a half, we could take this denominator, which is really under this radical sign, isn't it? Because it's really the square root of 1 divided by the square root of 2. We can multiply this whole thing by this denominator's value of a square root of 2 over square root of 2. And what will happen is we'll end up removing the square root sign, the radical sign, from around the 2. 1 times the square root of 2 is the square root of 2. 2 times the square root of 2 is the square root of 4, and the square root of 4 is 2. It's 2 times 2. So now the radical sign's gone, see? Let's try it again. We've got the quotient of 3 and the square root of 5. We want to get rid of the radical sign here, so we can multiply the numerator and denominator by that square root of 5. Up here we get 3 times the square root of 5. Down here we get the square root of 5 squared. See? Because we have 2 of them. And because that has a little 2 exponent, and there's really a 2 root out here that's invisible, isn't it? We can remove this radical sign because 5 times 5 is 25, and the square root of 25 is a 5. So we got rid of that radical denominator. See? He's pesky. We just don't want him in our math, okay? So the first thing I would do is look for the root. This is a cube root. So we need to make a cube out of this. So what could we do? Well, a 9 is a 3 times 3. So we can multiply it by 3/3. That's going to give us our third 3. See? We needed one more 3 to be a cube. 3 times 3 times 3. See? 7 times 3 is 21. We multiply the radicand by that 1, the 3 over 3, to make the denominator a perfect cube. Now we've got the cube root of 21 over 3 cubed. See? That removes the radical sign from under the fraction bar. See? We can multiply the radicand by a 1 either inside or outside the radical sign. So if you saw up here, I multiplied it inside the radical sign. See? We can also split it up so that they're separate. See? We can multiply the numerator and denominator by this square root of 5b. This gives us 2 times 5 times a times b. And this is squared because it's under there's a little invisible 2 here, isn't there? This is going to be the square root of 5b times the square root of 5b. And multiplied together, we're going to get 25b squared under the radical sign. And the square root of 25 is a 5. And we've got this b squared. We can take away that little 2 exponent because it's under a square root. And we just get b. And remember, when simplifying an even root to an odd exponent, we can use absolute value bars on the variables. So this went from an even root, because there's an invisible 2 here, to an odd one, because it's b to the first power, and a 1 is an odd number, right? When simplifying an even root to an odd exponent, we use absolute value bars on the variables, unless we know it's a non-negative, okay? So here's an even root of 4, and it's being simplified to just an x, which is really x to the first power. So we're going to put that x inside of absolute value bars, okay? Some teachers don't require you to do it, but many do, and if you see it as an answer on a test, you want to make sure you know what you're doing and why they're there, okay? Went from even to odd, all right? Let's take a look at this one. This 4 is really a 2 squared, isn't it? And then we have it x to the 5th, and we've got our fraction bar, we've got the square root of 3y cubed, and we need to find some perfect squares here. So this x to the fifth can be x squared squared, right? X to the second power squared. That'll give us 4 of the x's. And then this straggler right here will give us the fifth one. And because this is a perfect square and that's a perfect square, we can pull him out of the radical sign. But he's not a perfect square, so he's got to stay inside. So we've got 2x squared times the square of x. See? We got to pull out perfect squares from here, and 3y squared can be 3 times y squared times y. That's the 2 y's, and that's the third one, see, for that 3 exponent. So that means we could pull him out of the square root radical sign, see? So we've got y times the square root of 3y, okay? The 3 and the y, this blue 3 and y, or green 3 and y, are not perfect squares, so they stay inside of the radical sign. So now we're going to go from here, okay, and now we're going to multiply by a 1. Now, we're not going to multiply by y times the square root of 3y. We don't have to multiply as 1 using the denominator. We can choose any value as 1, whatever is going to make a perfect square. And what would make a perfect square here to get rid of this radical sign would be another 3y, wouldn't it? We need a 3 times 3 and a y times y to have that square, right? So we're only going to multiply by 3y for the numerator and denominator. See? Now we get y times 9y squared. And a 9 is a 3 times 3. So that means we have 3 times y, because that's what the y squared is. And when we simplify it, we get 3y squared at the bottom, see? On the top, we're going to get 2x squared times 3xy, see, for the numerator. What we're doing is we can multiply by, as a 1, any number as a 1 that will clear that radical sign. So we didn't have to do it by the denominator because of that extra y there. We just did it by the 3y, see? So I'll show you again. We're going to choose our value for 1. We look at our radicand. We've got a 9x. And a 9x is a 3 times 3 times x, isn't it? But we need 9x to be a perfect cube. We need another 3, so it's 3 times 3 times 3. And we need 2 more x's. We only have 1 x. We need x times x for it to be a perfect cube because this is a cube root. And in order to get rid of that radical sign, we need to find a cube root. So we need to multiply this by 3x squared. See? Right now, all we've got is this. So we need a 3x squared to make the rest of our perfect cube. See? So that's what we multiply it by, the cube root of 3x squared over the cube root of 3x squared. Now when we multiply straight across, we get the cube root of a times 3x squared, and we get the cube root of 27x cubed. 27 is a perfect cube, isn't it? And because we chose this as our value for 1, we made a perfect cube for our denominator. So now this can be rewritten in a better order, so it says 3ax squared, right? Tuck the a back behind the 3. And 27 is a perfect cube. It's 3 times 3 times 3. It's 3 cubed. See? So now this has a 3 exponent, that has a 3 exponent, and we've got a cube of 3. We can pull all of that off and just have the cube root of 3ax squared over 3x. And we got rid of that radical denominator. It's gone. He's such a troublemaker. We got rid of him though, right? So sometimes we need to multiply by something other than what's in the denominator. Sometimes we just need to figure out what it needs to be multiplied by in order to make it that perfect root. Even if you have a 4th root or a 5th root, figure out what that denominator needs to be multiplied by. And if you have to write it out like this, then do it and circle what you've got and factor out what you've got. That's a 9, so it's a 3 times 3 and an x. What do you need? See? Okay, our next video is 7.4c. We're going to talk about conjugates and multiplying by 1. We talked about conjugates in Algebra 1. We touched on it a little bit. So I'll have a link to that Algebra 1 video for your help. And I'll add this to the Algebra 2 playlist. And I'll have the link to the factoring review video we did back in 5.6. And I'll have a link to all the previous Chapter 7 videos that we did. Okay? A lot of links. The deeper we go into each chapter, the more links there are in the description, right? So try this. Try figuring out what you would need to change a denominator so that it would be perfect to that root, okay? I bet you can do it. All right? I'll see you next video. Bye.